Hello everyone, welcome to these videos. Today, I would like to present our work on graph neural networks for decentralized multi-robot path planning. This is a collaborative work between Polo Lab at University of Cambridge and Ella Lab at University of Pennsylvania. The main goal of this work is to apply graph neural networks to enable implicit communication between robots for multi-robot path planning. First of all, why are multi-robot systems interesting? Multi-robot systems are able to overcome the limited ability of single robot systems to handle large-scale tasks. Examples of this include the use of multi-robot systems for automated warehouse, search and rescue, and connected self-driving vehicles. The essential requirement of all of these applications is the capability to navigate individual robots to their target location without collisions. There are different approaches to find a coordinated plan for multi-robot systems. Centralized approach requires a central computer that gathers information about individual robots, including their goals and different constraints, which is used to compute a joint plan for all the robots. Decentralized approach do not require a central unit where the coordinate solution is computed based on local observation and message passing between individual robots to communicate the goal and constraint on the feasibility amount of robot. In this work, we are interested in achieving decentralized path planning, and we will demonstrate how we use graph neural network towards this goal. In our method, we formulate the multi-robot path planning problem as a sequential decision-making problem, where at every time instant, each robot takes an action toward its destination based on a local observation and the message that it receives. We aim at training our decentralized policy to imitate an expert algorithm that knows the information about the start and goal position of all robots, as well as the full environment map. The oracle algorithm that we use is called CBS, a collision-based search algorithm, to compute optimal paths for all robots in a given world, which we then use for training. In this paper, we apply graph neural networks to enable information sharing between neighboring robots. I just want to highlight the difference between the convolutional neural networks and graph neural networks. Generally speaking, graph neural networks are an extension of CNN for graph data. An image can be considered as a special case of graph, where the pixels are connected by adjacent pixels. The 2D convolution takes the weighted average pixel values of red dot along all its neighbors. The neighbors of the node are ordered and have fixed size. Graph convolution, on the other hand, use aggregate values of node features of red node along its neighbors. Different from image data, the neighbors of a node are unordered, and the neighborhood size can be variable. In our case, when a red robot takes its actions, it uses information provided to it by GNN. In this paper, we use the fx to define node feature of robots, which is a high-dimensional representation of input tensor. We use adjacent matrix to express relationship between robots mathematically. The adjacent matrix is computed based on communication radius that define communication topology. A is the trainable parameter. The graph convolution operates on graph data to take the average sums of node feature of blue node along its neighbors, green node. As the number of communication hops increase, the GNN are able to extract information for a larger range of neighbors. We have four main modules. Data generalization from our expert algorithm. Transform the offline dataset into 3-channel input with partial observation constraint. The decentralized framework consists of a convolutional neural network that extracts adequate feature from local observation, a graph neural network that communicates this feature among robots, a multi-layer perceptron to predict action. The predicted actions are paired with the ground truth action from an expert algorithm at each time step, and trained by minimizing the cross-entropy loss. To train our model, we propose a supervised learning approach based on expert data. We designed the following process to generate expert data based on the conflict-based search algorithm, CBS. Firstly, we create a grid row with certain width and height and random place static obstacle. For each grid row used in training, we generate random cases as shown in the figures. We assign different pairs of start and goal position for all robots. We will filter duplicated and invalid cases. In each case, we will deploy an expert algorithm to compute ground truth path. Hence, we can transform the path into sequential pair of robot state and each actions. Next, we will present a videos about how we obtain input tensor with partial observations. In a 92 x 92 grid row, the robots are moving to a grid with the same color. Let's take the robot 9 as an example. We know the current position of the robot knight. We set a local field of view of the robot. When the goal position is out of such field of view, we will draw a line between the robot's current position and the goal, which will intersect with the boundary of the field of view. We call it the point of intersection as the projection of the goal on the field of view. This helps the robot to move towards its destination without requiring a full map of the environment. Then we can transform the information within field of view into an input tensor with 3 channels. The first channel, partial observation of the environment. Second channel, the position of the goal or its projection on the boundary of field of view. The third channel, self-agent at the center with other agents within its field of view. By subtracting the robot position at next time step with current position, we can obtain the action paired with the input tensor at current position. We will repeat this transformation across all robots at each time step and repeat across the maze span T at each case. Now we will introduce our new network architecture. The decentralized framework consists of a CNN for feature instructions, a graph universe that communicates these features among robots, and a multi-layer perceptron to predict action. Then we obtain the input tensor Z from robot I at time T. The convolutional neural network will operate on it to extract ethical features into X-type. Within a distance-based communication radius, the GNN can the average sum of node features of the node I along its neighbor J based on adjacent matrix at current time step. For example, when k equal to 1, robot B only has its own information. When k equal to 2, a one-hop neighbor of robot B includes robot A and C. After the graph operation, we obtain the feature xt containing the hyper-representation of node feature of B, A, and C under k equal to 2 setup. The feature xt will pass into the action policy and NLP to compute the probability distribution over the 5 motion primitive up, left, down, right, idle. The predicted actions is paired with the ground truth actions at the same time steps, which can be trained by the objective to minimizing the cross-entropy loss. This procedure summarizes the formulation of multi-robot path planning problem as a sequential decision-making problem. Let us have a look at how communication channel is built during the path planning. Let's take the robot knight as an example, and the communication radius is 6. This means if the distance between the robot knight and the robot is less than 6 grid cells, we can build a communication link in between. These robots are the one-hop neighboring robot for robot knight, and the communication link is represented as a red line. Then we call the neighbors of the robot knight is the two-hop neighbors. We used an orange dashed line to represent this. This video also clearly shows that at every time step, robot knight only obtains information from a certain number of robots rather than all robots in the row. Given the decentralized nature of our framework, the trained models are efficient in the sense that their computations are distributed among robots, demanding only the communication exchange within neighboring robots. Let's go back to the pipeline one more time before we introduce the inference state. We randomly generate different grid row and random cases and compute solutions for all 30,000 cases by an expert algorithm offline. Then we split them into training, validation, and test set. Then we transform offline data into 3-channel input tensor with partial observation constraint. The input tensor passes through our models where the CNN extracts a feature from the input tensor, and the GNN fills the information of the feature among the neighboring robots, and the NLP to predict action. Hence, the state and action pair can be trained to optimizing the trainable parameter in the architecture by minimizing the cross-entropy loss. Once we have a trained network, we evaluate its performance at inference state. The input tensor Z of robot I at time t will pass into the trained network through a forward pass and predict an action. Then our inference algorithm will check whether the predicted action results in collision between the edge of the grid row and the static obstacle, or whether there is inter-robot collision. If so, the robot will stop to avoid collision. This mechanism is called collision shielding. If the predicted action doesn't cause a collision, the robot will key the predicted action and check whether the robot reached its destination by then. If not, the robot will update its state and input tensor and go to the loop again, until all reach their goal or the loop exceeds the maximum step. Once the loop finishes or breaks, we can recall whether it is a success and the flow time of the predicted path. To evaluate the performance of our method, we perform 2 sets of experiments. Train and test network on the same number of robots. Train the network on a given number of robots and test on previous unseen team size, both larger and smaller. We consider two key performance metrics, success rate and flow time increase. The success rate is the metric to evaluate the completeness of the network. It is the proportion of success case among all the cases in the test set. A case is considered successful when all robots reach their goal prior to timeout. Flow time increase is used to evaluate the optimality of the predicted path compared to the ground truth path. In the equation, Ft star is the flow time of the S-bar. Ft is the solution from the network. Delta Ft is computed by the sum of executed path length may be larger than the sums of S-bar path length. In the first experiment, we train and test the network on the same number of robots. We train a model for 4, 6, 8, 10, 12 and test it on the instant of same robot team size. In each experiment, we vary the number of communication hop 1, 2, 3. Note that for K-1, there is no communication involved. We see a drop in performance for large team, but this drop is much more pronounced for non-communication GNN, K=1. There's a small but noticeable improvement as we increase the communication hop from K=2 to K=3. The GNN with data aggregation, unlike S-bar, can further improve the performance of our framework by aggregating solutions from the deadlock and live lock scenario. The results show that our framework generally outperforms the reaction-based algorithm, discrete outcome, in terms of success rate and flow time increase. The table specifies the number of robots trained on across the row and the number of robots tested on across column. The generalization performance of the network is visualized by a heat map, which maps the performance onto a color range from purple to red, where purple indicates the best performance and the red indicates the worst performance. First, we see for the most column, the performance improves as we increase the size of robot team during training. Also, comparing performance across column for a fixed row, we observe that as we train the networks with increasing large robot teams, the network tends to generalize better across any unseen instance, larger as well as smaller robot teams. Perform subsequent experiment on larger robot team to further test generalization. Figures show that our network trained on only 10 robots scale up to 6 floor size. We train our model on 20 by 20 map with 10 robots and test it up to 60 robots in different grid maps with same effective density. Notably, the results show no significant decrease in performance. Let us watch another video by testing a network trained by 10 robots on 40 robots in unseen script row, a benchmarking map from Namfield. The panel on the left, all robots move according to the path computed by S-bar algorithm, CBS. The panel on the right, all robots move according to the path computed by the proposed networks. Let us take robot 20 as an example. The red line showed the one hot communication neighborhood of robot 20. The orange dashed line represents the two hot communication neighborhood. This video also clearly shows that at every time instant, the robot 20 only obtains information of certain number of robots rather than all robots in the world. The robot can move in a cooperative manner with the help of communication. We propose an end-to-end learning-based decentralized path planning framework by utilizing a GNN to process partial observation information and a GNN to implicitly share information between neighboring robots through the graph operation. Our results show that we are close to achieving the same performance as the optimal search-based algorithm. Importantly, we show that our model generalized to previous unseen cases involving much larger robot team and previous unseen environment. This enables us to solve large-scale cases that are intractable by classic method. Thank you for your attention, and I look forward to hear from you.